Okay. And remember lab, we have wet lab on Thursday. So don't forget your PPE and your pre-lab, okay? If there's any question about that, please feel free to reach out. Okay. So I think last time we pretty much talked about how cycloethers, they're particularly reactive with base. Remember, ethers are not usually reactive under basic conditions, and that's because there's not really a good leaving group, okay? So we saw ethers react this way. But now let's talk about exactly how these mechanisms occur, okay? So, let's start with the mechanism of ring opening. Of epoxides in basic conditions. All right, so this will occur under a SN2. So I'm going to put this in quotation marks because it's not exactly like SN2, because usually you don't have a epoxide. Okay, so good nucleophiles. All right. So we're going to draw a bold bond here to the epoxide. So that's my wedge bond. The OH minus here is going to attack and immediately break this bond. It goes back to the oxygen. All right. All right, guys, let's settle down there. Thank you. All right. So remember, it attacks from the opposite side, so that's why the bond has turned to a dash. It's inverted to stereochemistry. Okay. But in this example specifically, there's really no stereochemistry because it's at first it was symmetrical, but now it's going to be inverted here. So O minus. And then usually the conditions are water or acid. So water will take the position here, and you will abstract the hydrogen from water to get the final product under basic conditions. All right, and then you get hydroxide as a byproduct of the last step, which is hydrolysis, donation of the hydrogen ion. Okay, so the mechanisms between acid and base, they're very similar. You're getting the same products pretty much, but if it's not symmetrical, you're going to get different what we call regioselectivity. So the nucleophile will add on one side of the epoxide versus the other. So it's not always the same. All right, but now let's talk about the other type of mechanism here. So the mechanism under acidic conditions. So you can open these both in acidic and basic conditions. And for ethers, we only need to remember that this only happens primarily to epoxides, so that's the fastest. This does not happen to 6-membered rings, 5-membered rings, and 4-membered rings. They're much harder to open up in basic conditions, okay? So just worry about this for epoxides, the 3-membered ring with oxygen. All right, so we call this SN1-like. And the reason we call it SN1 is because we'll see that in more complicated examples, the opening epoxide ring looks like it favors the formation of a carbocation. So we'll see that. Okay. So first thing we do is, all right, so what's the first step if we have acidic conditions? All right, let's have our acid here, H3O plus. All right, what do you guys think? What happens first? Yeah, so one of the lone pairs on oxygen is going to pick up acidic hydrogen and then transfer that away from the acid. You get out water, and now you're going to get your protonated epoxide here. So you're going to get a protonated epoxide. So now that's a great leaving group, okay? Okay. All right, so the reason I say it's SN1-like, it doesn't actually form a carbocation, so water. Okay, so we're going to put water here. And we're going to show it attacking from the bottom face, and this will go back to the oxygen atom, like that. Okay, so this reaction probably won't go back, so we put it this way. We draw it this way. Okay, so it's going from the bottom face. Now you're going to have a protonated water molecule, and then you're going to still have the wedged OH group here. Okay, and then the last step here is you're going to have lots of water. So water, another water molecule is going to come around, take away the proton, give it back to the oxygen, the electrons, and you regenerate your acid catalyst, which is H3O plus. All right, so those are how the mechanisms work. So they look the same, but the steps here are important. So you don't want to attack you don't want to use, for the first one in basic conditions, you want to open up the epoxide first, then add the hydrogen. You don't want to do the hydrogen first. And the reason is that if you try to, you might get confused on like where the selectivity lies. So it's always base first, and then the acidic hydrogen is going to be accepted by the alkoxide there. All right, are there any questions on those mechanisms? So they look very similar, but the truth here is in the details. Yeah, Catherine.
Where does the hydroxyl come from in the?
Oh yeah, so this is from sodium hydroxide. So there's sodium on here too. So we add sodium hydroxide first, then we add water.
So you have, you open the epoxide first and then protonate for basic, but then you can do the opposite for acidic.
Yeah.
Protonate first
Mm-hmm.
and then.
Yes. And the reason why we don't do the opposite, because if we protonate it, the hydroxide is just going to attack the hydrogen and just get it back. So it's pointless. Yeah. So something that's very acidic and very basic, they'll just react right away. That's even faster than nucleophilic approach. Yeah. All right, now let's talk about regional selectivity here. Okay. So I'll give you an example, and then I'll do the mechanism again, so we have more practice with drawing these arrows. Okay. So what if now our epoxide is asymmetrical, not equally substituted? So this is where we get into cases where the nucleophile will only add to one side exclusively, okay? So, our last topic for ethers here, regio selectivity. So what do you think regio means? Regional, okay. Like the region, like the area around something. So it goes to a specific side. All right. All right. So I won't necessarily give you cyclohexanes all the time, but they're pretty common, so kind of like them. So I think they're good examples here. Okay, so now it's asymmetrical, right? We have two chiral centers. So where the epoxide are, that's our chiral centers. All right. So you always know you have basic conditions because there's a metal ion involved in the reaction. All right. So let's use sodium epoxide. So here's my sodium alkoxide, good base. And my solvent is ethanol. Remember, the acting nucleophile is the one with a charge, and that's above the arrow, okay? So if you carry out this reaction carefully here, you will get this product where the epoxide has opened up, okay? And it has attacked what kind of side? What would we call the side on the bottom there? Least hindered, more hindered. Least hindered, more readily available, right? That looks like SN2-like conditions. So we're going to say SN2 selectivity. All right, remember SN2? Good nucleophile prefers the most unhindered substrate, so unhindered position here. All right. So let's explain how this mechanism works and how we got the oxygen atom protonated. All right, basic medium is the basic means your pH is basic. All right, so SN2-like conditions. Least hindered substrate. All right, so let's draw our product again, and let's see if we can put in the right arrows. All right, so my nucleophile approaches. So use your nucleophile. So I'm going to use my epoxide here. Put in your charge. All right. Which side should I attack? The bottom. So it's going to go from the bottom face, okay? And then this is going to kick back out. You're going to break the ring from the epoxide. And what you get here is... So when you're drawing a cyclohexane, it's a lot easier if you just switch the dash bond or wedge bond for the incoming nucleophile. So here, well, it was coming, I approached from the bottom face, so this is going to be a dash bond to my ethanol here. Okay, so where do you think I get well, I'm almost done, right? But I'm missing the hydrogen. Where does the hydrogen come from? The solvent, right? The one on the bottom. Epoxide can't donate a hydrogen. There's no acidic hydrogen, so it has to come from ethanol. So let's write ethanol. You see here, the final product, we got the protonated alcohol, ether alcohol. And what's left over is the conjugate base of ethanol. So basically the group that left after the base, the acid was donated. All right, so that's basic conditions. So this mechanism, not too bad. You're doing like 3 arrows. So that's something we have to think about. Think about the mechanism, all right? That can help you determine the final product. And if you're not sure if the final product has the correct stereochemistry, just remember this is like an SN2 reaction. So the stereocenter should have changed at the reacting carbon atom. Okay, are there any questions about the basic conditions? So this is unique because you can actually get different selectivity based on the conditions you use, acid or base, so they change. Yeah, Catherine.
So with the final product, it can't repeat though, even though there's like a starting nucleophile or.
Oh, what do you mean repeat?
Because we end up with the ethanol, the O- side, which is the thing that we started with to help.
Oh yeah. It won't react with the product. It'll just react with more starting material, if anything. Yeah. All right, good question. So actually, if you add acid to this, you can actually go backwards, I think. But don't worry about that. Okay. So this is an interesting product. So this is an ether alcohol. So you could potentially do more chemistry with this if you wanted to. But usually when you get this is usually a product you would want. All right, so your product here is an ether alcohol. But remember, if our nucleophile is cyanide or N3 minus or acetate, I'll just replace my ethanol group there with the appropriate nucleophile. So you can get a wide range of different products that could be of great use for whatever reason. All right. Okay. Now the acid condition one. This is a little bit more involved. Okay. All right. Now let's talk about acidic medium. So acidic medium. All right. On your homework, there's a few problems that will ask you. You have acid conditions. You have a primary position, and then you have a secondary position. All right? It's a trick question, okay? So I'll present to you the 2 obvious pathways here. Least hindered, basic conditions, least hindered side. Acidic conditions, tertiary position. It's going to go to the tertiary side, as we'll soon see. And now, if it's in between, if you have a primary position and a secondary position, the homework's going to tell you. You might think, it's secondary. We should go to a carbocation. But that's not the case. Because remember, secondary positions for carbocations, they can't decide if it's an SN1 pathway or an SN2 pathway. So you kind of have to go back to first principles. I'll explain what I mean soon here. All right, so we clearly have a tertiary position there. Okay. Now let's draw our epoxide here. Okay, so our only difference here is you're going to mix ethanol, your solvent, with a strong acid, H+. So this reaction will react for a bit, and you can either protonate the alcohol, but that won't get you anywhere because that's your nucleophile. So the next thing it can do is protonate the ether. So we're going to protonate the ether. All right, but first let's just draw the product. And you'll see here we'll get complete reversal of the selectivity, and you're going to get substitution at the opposite end compared to what we started with. You see here the stereochemistry has switched, so the methyl group is sticking out. And this OH, go over here. All right, so we have to explain this result. It looks like we just attacked the other side. But the stereochemistry switched as well. So it's still, it looks like SN1 type chemistry, but no carbocation has formed. It's still backside attack. Okay, so that's the weird thing about the epoxides. All right, let's go over the mechanism, show how this works. All right. Okay, my bad. Let's back up a bit. All right. All right, so what's the first step here in the acidic mechanism? So what's the first obvious step here? Yeah, so we had to open a ring, right? So ethanol is not a very good nucleophile. It's weak. It's very weak. So we need to make a great leaving group first. So what we're going to do here is the lone pair is going to protonate the oxygen, and then you're going to get a oxonium ion intermediate. Okay. Okay, so there's two different transition states we can have. Okay, so let's draw the structure again. Okay. All right, well, we know this bond is breaking, right, to the epoxide. Okay. So, and then in the transition state here, this is going to be a delta positive. But we know here that as this bond is breaking, a delta positive charge is forming. Okay, so we have that situation. And then, so we have this situation, right? So which side do you think, if a positive charge did form on the carbon atom next to the epoxide, which carbon you think is able to stabilize a positive charge better? Is it the tertiary carbon over there? Or is it the secondary one? The tertiary, so that's more stable, okay? So what ethanol could do is that it can attack this position, okay? And break this bond here. And this is actually what we see here. So this here, we see a longer CO bond breaking. So that bond is being elongated because it's more stable, okay? So at this position, what we have here is more partial positive charge. Okay, and this is actually what leads to our product. Okay, so it goes through this transition state, so we can kind of put this as a, well, we'll just leave it like that. Okay, so you have two options, right? This position, and then when you do that, it's going to attach through the bottom of the epoxide. So now we have attained the positive charge. The methyl group is sticking out, and we get this group here. All right, and the last step, another ethanol molecule will come around and pluck off this hydrogen, and then you have gotten to the final product here. Let's just put this wedge bond there. Damn it. All right. All right. So this is one way, right? So this is at the more substituted side. But what if we go through the less substituted side? Okay, so you can also have this situation. Let's just draw out both situations. All right, so here's the epoxide. What if this bond were to break? So let's put dotted lines there. We have a buildup of partial charge. But is this partial charge as stable as the tertiary position? What do you guys think? No, right? So here, this CO bond is shorter. That means it's stronger. All right, so you have a shorter bond, but that's stronger, okay? So that's going to be harder to break, okay? So the ethanol could go in this direction. It could do this, all right? And then what would you get is you'll get the regional isomer. All right, so the OH is on the other side. But that's not what we see in reality. All right, ethanol. Oops, let's go back a bit. Ethanol could take this hydrogen, okay? And you would get an expected product here. But this is not what we see. We don't see this. This doesn't occur at all, okay? So this selectivity here is not observed. And it's because this bond here is much shorter in the transition state than this bond. And this difference here is what drives the reaction towards one product. Like that. All right, so I want to make a few notes here, okay? So what I want to say is that the full positive charge on carbon does not form. Okay, so there's no carbocation, but this the selectivity kind of gives you the false impression that it does form through a carbocation, but you don't see a racemic mixture, so you can't say that. Okay, so the key point here is that there's more positive charge on more substituted carbon atom. Okay. So that's the selectivity we see. Okay, so you have a tertiary position. So let's just mark these positions here. This is a tertiary position. Okay, so that's why it promotes that one. And then, so yeah, that's the tertiary position. So tertiary position, you're always going to go to the more substituted side for ring opening. If for the least hindered side, under basic conditions, that's where you would go if you had basic conditions right here. All right, now the problem is what if you have a situation like this? What if you have a epoxide like this? Okay. All right. Well, you have a situation like this, right? What would you think the product would be? Where would the epoxide open? This carbon, right? So you would think it would be at this carbon. Well, this position is actually secondary because there's only one other carbon substituent. So there's one carbon here and then one carbon there. So it's actually still just tertiary, secondary. So you might think this would open the usual way. You might think it'll just open, let's see, like this. You might think it would just do that, right? It'll open up at the more substitute carbon, but that's not what you get. So this is actually not the product. All right. So the sequence of events here is you're still going to protonate first. All right. You're still going to protonate here, but we got to remember what's the problem with secondary, alkyl halides is that you can't decide if you're going to do SN2 or SN1, right? So secondary carbocations are not as favored, right? So this would be a secondary carbocation, so secondary C+, not as stable as tertiary. So the BR won't actually, well, let's think about what BR does, right? BR, what would we classify that as? Weak nucleophile or strong nucleophile? Strong. So Br minus is a great nucleophile. So very great nucleophile here. And remember what that chart for SN1, SN2, E2, and E1. Good nucleophiles, but weakly basic. They prefer SN2 type conditions. And SN2 type conditions, which side would you attack? The primary or the least hindered or more hindered side? Least. So this actually goes this way. So even though it's acidic conditions, if it's not tertiary, you can expect the opposite. But this is just something you might see on the homework, so I'm just giving you a heads up. All right, so what you get here is OH. Okay. So you get the opposite regional selectivity. So this is the product you actually form. All right, so that's something to keep in mind for your reactions here. Okay, so be able to draw the mechanism, so you might have to show some arrows, and then be able to predict the product. All right. Let's see here. I want to, before we conclude this chapter, I want to show a little picture of something. Do I have it though? Maybe I don't. Aha. All right. So epoxides also has biological activities. All right. So take a look at this compound. You don't have to draw this. You don't have to. All right, let's see here. So this is what we call a polyaromatic compound. This is found in gasoline. And this is why you shouldn't burn gasoline too much, because if you inhale this, your body will oxidize this to this compound. All right. So by just looking at these two compounds, which one you think is more water soluble? My structures are getting worse by the moment. Yeah, the second one. So you breathe this in, your liver will get to this. We'll try to metabolize this. So this is called a diol epoxide. Okay. Well, if this accumulates in your body, this is a great electrophile, right? So what happens if you have some biological compound here? And it's nucleophilic. What do you think is going to happen? What do you think is going to happen if this gets into your body, it goes into your cell, and it approaches DNA? Well, DNAs have amines on them, right? Oxygen atoms, amines, side chains. They're nucleophilic. They will attack this epoxide. All right? And that will just repeat over and over again, okay? Because look at here, you can also close this to an epoxide. So every molecule you do here, you can also form epoxides on any of these rings. And eventually you can mutate DNA, and that's how you get cancer. All right, so we burn this, it's in the air, we burn this, all right? If you burn gasoline, you can get some of these. These are particularly toxic. So that's why they're trying to ban them. All right, so that's our biological look into why epoxides are important, okay? Oh, but one thing I want to bring back, we had a question about nomenclature last time. I just wanted to revisit that, okay? So let's go back to, let's see, what was it? I think it was 24. Here, this one. All right, so remember when we named this compound? Someone asked, what if there's an alcohol in the same compound? So I did some digging. In truth, I just used ChemDraw. But it helped me refresh my memory here. Okay? So let's say we have this compound. We already drew this compound on the left. But what if there's an alcohol in there? Well, it turns out the naming is not that bad. Okay? But your parent name changes to an all. So our parent name would be, all right, you have to be careful though. So it's very similar. 3-bromo. 5, so here we'll count them here. So this guy still gets the 1 position. 2, 3, 4, 5, 6. And that's because it's in the ring. The oxygen's in the ring. So it's still an oxa group, okay? So 5-ethyl. This is purely for our entertainment here. Oxa, so it's still oxa, all right? Now, cyclo. Hex. All right, let's scoot here. All right, so there's no other way around it. I tried to do this myself. If I put the number for the alcohol outside, it gives me a completely different compound. So we have to include it inside the ending here. So hexane, so it's a hexane. And where's the position of the alcohol? 4. So 4-all. So you can still name this according to IUPAC, but alcohols will take a back seat to the ether because that's part of the ring. Now, if you had a linear ether, and an alcohol, then it'll be called alcohol. But since it's a cyclic ether, we have to name it this way. Okay? All right, those are the only ethers you have to worry about, so don't worry too much about any other ones. All right, that is alcohols and ethers. Chapter 17 and 18, you don't have to worry about sulfides. We already talked about sulfides in SN2 type chemistry, so you don't have to worry too much about that. All right, let's take a little break before we jump into alkenes and alkynes, okay? Yeah, sure. Hey, what's up?
Since I wasn't able to test the quiz on Thursday, can I take it after class today?
Yeah. Thank you. We are. So just prepare the pre-lab, and it's T-pentyl chloride. It's in the lab manual. Yeah.
has to be postmarked by today. Yeah.
You can
You can even, they accept them here.
Yep.
Yeah, there's like a box. There's like a Are you sorry, California? Yeah. Okay. Yeah. Where are you registered?
So member disagree agreement. Go action this
Where?
No, you'll form a bond to the phenol group. And this will be an alcohol. Yeah. That's usually how we form alcohols. Because we need to form carbon atoms. No, there's no alcohol. It's just alcohol. Yeah, and then don't forget there's another bond there.
Like on her door.
Yeah. And then there's
I like that.
There's a bond here coming off the phenol.
There is always someone there. I think it's someone like that. Give like,
Oh, this bond here?
She's been here for a while.
We're gonna, right there, you're gonna draw phenol group.
So much.
And then don't forget the yard.
What's so funny is they're like,
Alright, so that's the first part, right? We'll move on to this group, and then the OH switch protein next.
oh wow. And so like Chuck Schumer, who was the minority leader in the Senate or the House.
Yep, right.
Like,
That was
endorsed him, even though he got his Democratic nominee. Oh wow.
Yeah, the DR doesn't react.
Did you buy it for today? Yeah, due before 5.
Well, that's not what we're saying now, so, you need a bond.
Or I would like to, yeah.
Oh, yeah, it does.
I
You
should
had
do it
the,
online. Right, save paper. Well, this answer, I don't think this doesn't affect the government shutdown, does it? This doesn't affect the government shutdown.
yeah, so that's.
This is for states, so like.
Yeah, so this forms a good leaving group here. You form a, inorganic ester, and after you say leaving group, and it doesn't. Yeah, it's a pH thing. So. Yeah, it is in practice. Yeah. Remember, this is a new file. Carbon, the carbon on here is making charge. It's a good new file.
You're going to school I mean, I'm a bit, but I just put on there, because before that, for like a tan, so last time we can have $70. Or that lasts a week and a half, so I have to get a big one, to eat every 3 hours. Yeah. Oh, yeah. Everything crashed and stuff, Look, there's like, this is the highest, bankruptcy. Yeah, my parents went through bankruptcy and actually got to keep their house, they just paid double payment. Yeah. Or something crazy. My parents, but they were like, stressed out.
should finish this movie today.
It's pretty apparent for we wear. And it, don't you have to do special, you have it really very white down. Oh, and that I don't have straight hair. That's where they have like, if they curly hair, it was a perm. It was very easy. Like oiled. Oh, okay. So like it was like, no matter even he said like the girl was gonna be there. Yeah. So like for mine, it was like, unless you put it into the product. Even then, like, when you had to do it's hard to it's really brave that it tones. She was such a tiny thing. She did not. It's so tight. I love my hair. My mom even had a braid. My nannies. I don't want hair.
I remember one time she made a braid on me, and it was like the middle braid right here. And my sister made fun of me because she said it looked like a dinosaur.
All right. Well, let's resume now. That'll be fine. Okay. So, the last thing we'll talk about are alkenes and alkynes, but first, the differentiate, and we'll just talk about alkenes first. All right, they're considered more important. If we don't get the alkynes, I'm not really concerned about that. Alkenes are way more prevalent. They're in your water balls, plastic water balls. Alkenes are in there. All right, all kinds of plastics. You know, frisbees, benches, made out of plastics. They have some kind of alkene in there. All right, so they're used greatly in polymers. All right, so alkenes. Naming the alkenes. Can't forget nomenclature. All right, so naming alkenes is very similar to naming alkanes. Find the longest chain with the alkene, and then the ending will change based on the functional group. So find the longest chain with the double bond. Okay? So you're going to name the compound. So name the compound with ene ending. All right. So for example, the simplest alkene here is ethene. All right. So ethene is not only a important industrial chemical, it's also found in living things as a signaling sensory molecule in trees. Okay, so not just used industrially here. So ethene is a common name, ethane. Okay, and then the common name here, the most commonly referred commodity for this alkene is called PET plastic, polyethylene terephthalate, and those are the plastics found in plastic water bottles. Okay, so that's ethylene's the common name. All right, so how do we number the chain? What do you guys think? I think it takes a similar pattern to how we saw nomenclature all semester. So we're going to number the chain starting at what end? Yeah, so just closest to the substitution, right? Starting at the end, closer to the double bond. All right. Now, if there's a tie, you're going to start at the end, closer to the first substituent. All right. So if we have a tie, if there's a tie, okay, you're going to begin at the end, closer to the first substituent. All right. And then for cycloalkanes, so for cycloalkanes, bless you. Sorry, not alkanes, alkenes. I meant to write alkenes. For cycloalkenes, they're always between C1 and C2. So they'll always be between C1 and C2. Okay? And just like with alkanes, you number the chain the same way. So number the substituents, okay, with the lowest number. All right. We'll do a few examples towards the end of this discussion here, okay? So for three, if you have polyenes, so for any alkenes with multiple double bonds, all right, we're going to use the endings. So use the endings, diene, triene, tetraene, and etc. Okay? All right. So there's polyenes, and then the alkenes. We kind of named them and numbered the substituents, similarly how we did for alkanes. All All right, so how do we name di-substituted, tri-substituted, and tetra-substituted alkenes? There's geometry considerations we have to be aware of. So if you have di-substituted alkenes, you can label them as cis or trans. So identify cis or trans isomers. All right, so this is for di-substituted alkenes. Okay. For tri-substituted or tetra-substituted, for tri-substituted or tetra, alkenes, we have to use a new notation, E/Z notation. All right. So E and Z notation is very similar to R and S. So remember R and S, we listed the priorities around the chiral center. Now we're going to list the priorities around the double bond, and then depending on the order, we can get an E alkene or a Z alkene. Okay. So here, what we want to say is that the groups around double bond. Around the double bond, okay, assign similar priorities. So we're going to assign priorities similar to R and S, okay? So don't forget R and S, okay? So the top two priorities, so two higher priority groups. All right. If two of the higher priority groups are on the same side, all right. So that's called zusammen. In German, that means the same side. So that's Z. All right, that'll be on the same side, Z. Now, if they're on the opposite side, that's called German Entgegen, and that's opposite. E. So E alkene is when the top two priority substituents are on the opposite side of the alkene. Okay? All right. So we kind of, some nomenclature here. Yeah, Catherine.
What do you mean by on the same side, like, especially with
Oh, we'll get into that.
Okay.
Yeah, I'll get into that. Okay. And lastly here, option number 5, alcohols have preference over alkenes because of the oxygen atoms. So oxygens have precedence. So like precedent, like in court cases, they have precedence over alkene. So they're kind of more important, I guess. All right. So in this case, we named this as an alkanol. Name as alkanol. All right. And then like always, the OH group should be the lowest number, or should have the lowest number on the chain. So it should be at the lowest number on the main chain. Okay, so there we go. So let's do some examples of alkenes. So start on the alkene homework if you can, but first finish the alcohol one. So I won't start on this until maybe the weekend. But this one will be due on the 20th. Okay, so when exam 3 rolls around. So let's talk about some examples here. All right. So our alkenes here. All right. All right. So notice this alkene. It has 4 substituents, but we actually wouldn't name it as cis or trans or E or Z because there's a hydrogen here. Okay. So we're not going to worry about cis and trans or E and Z for this case. Okay, and I think the reason is because is this group here. All right, so let's find. So let's start simple here. So, what's the longest chain? I see 8. Does everyone else see 8? If someone doesn't see 8, please have your next door neighbor help convince you. All right, is there 8?
Yep.
1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 1, 2, 3. Good. All right. So now with the labels of substituents. So at the 5 position, we have an ethyl group. So let's write 5-ethyl. Okay. All right. What other substituents do we have? Yeah, 2,3-dimethyl. Very good. Okay. All right. And then I think that's it, right? What's the parent name? Yeah, and octene occurs where? What carbon? 3. So let's write 3-octene. So you can write 3-octene, or you can put the 3 inside of the parent name. But I'm just going to leave it like that. Okay. Yeah. So I avoided specifying the stereochemistry here in terms of E and Z, so we're going to do that in another example. I just want to start out simple here. Okay, does everyone agree with that name? Any questions? So that's the level you can expect for naming alkenes. Okay, so nothing too different, just now you're specifying where the alkene is. All right, let's do another one. Let's do a cyclic alkene. All right. All right. How would you start this one out? So what's the parent name here? All right, we got cyclopentene. Good. So remember, the cyclopentene always starts at the 1 position. So, well, let's think about this one. If we number it here, right? 2, 3, 4, 5. All right. Yeah. So this one's a little weird. You think you'll number it this way? Unfortunately, no. So you should start at the alkene carbon that is more substituted. That should get 1. So let's just reverse the order here. So 1, 2, 3, 4, 5. So we're going to use that numbering scheme in this case, okay? So remember, if there's a tie for the alkene positions, like in this ring, you want to start numbering at the position that's kind of like more bonded with more substituents. So more substituents should get the priority here.
But then you have to go to the next carbon in the alkene bond.
Yeah. So we'll just reverse the numbering. We'll switch 1 with the 2 position. So we're going clockwise now instead of counterclockwise.
Would you want bromine to be on a lower number?
Yeah, I would think so too. Yeah, I would think so, but I think it's because the alkene's more substituted. That should have the priority in this case. Yeah. So this one would be 5-bromo, 1-chloro. Okay, and then the 1 position. So if you have more substituents on the lower number, I think that's better. So the alkene and the chlorine are both at the 1 position. So that's better than saying 1, 2, or 1, 2, and 3, which, you know, it might not make sense in terms of the lower substitution standpoint, but in this case, we want the alkene to have the lower number and also a substituent with the lower number, so that would win out. All right. Yes, Captain.
For this example, how did we just choose 3 instead of saying dimethyl 3, 4? 'Cause if
Dimethyl?
carbon 3 and 4 both have like carbons 3 and 4 have the alkene between them. Will we just say?
Oh yeah. So you just start with the you just specify where the alkene begins.
Okay.
Yeah, you don't have to specify the form. Yeah. All right, we hear that. So the alkene, you only specify at the position where the alkene starts. You don't have to specify the 4. Okay. Good. All right, now let's do. Okay, I think this is. Let's do a different example. Now we're going to talk about priorities. All right, so here's my alkene. I'm going to draw out the carbons. Here's my alkene. All right. So we'll have to label priority. So the sides of the double bond, what I mean is you have this side, you have this side, and this side. All right, so let's compare the 2 substituents on the top quadrant. All right, what has higher priority, methyl or isopropyl? Isopropyl. So here is a low priority. So let's put the low priority, high priority. Okay. Okay. Now let's look at the bottom. Okay. What is high priority in this case? What is BG? All right. Yeah, I'm trying to think about this one. Okay, so which one would have... All right, let me just modify this one a bit. All right, so I think I made a typo here. We're going to do this thing, okay? So we're going to switch those carbon atoms, and now we have this group here. All right, what's has higher priority over here on the bottom half? Propyl or ethyl? So this group here or this group right here? Let me point that out to you. This group, which one has higher priority? Propyl. So this is higher priority. Lower priority. All right, so the 2 highest priorities, you take a look at them. Are they on the same side of the double bond or opposite sides? They're on the opposite sides, so this would be an E alkene, okay? So they're on opposite sides, so opposite sides. E alkene. All right, so now let's number this one. Okay. So 1, 2, 3, 4, 5. All right. So which way will we go? Will we go towards the alpha side or the... I think we want to go... Either way, it doesn't matter, right?
Why don't you go right to left?
Oh yeah, I think you're right. Let's go right to left. All right. Now we go. That makes more sense because then you ask yourselves, why did we go this way first? Okay, good. So how will we name this? So we know it's E-alkene, right? So E comes out in front. And then where are some of my substituents? So let's check this one. So what's at the 3 position? Yes. All right. And then what else do we have? For methyl. Okay. And then what else? 3 hep. Yep, alkene, so 3-heptene. Very good. All right, any questions on that one? Those are alkenes, okay? E-alkene and then Z-alkene. So if this propyl group was on the same side of the isopropyl group, this would be a Z-alkene because those 2 groups are on the same side. All right, very good. All right, let's try a few more. How will we name this one? So let's practice naming this one. So notice here you have 2 bromine groups on the same carbon, but you can't really label this as cis or trans or Z, E or Z, and that's because 2 of the groups are the same on both carbons, so they don't have really any stereochemistry. Okay, but this molecule is symmetrical, so. Doesn't matter if you put the bromine on this end or the bromines on the other end, you get the same compound. So what will this be called? So you have 2 carbons. What's the parent name there? Ethene, good. And then what are the substituents? Yep. And we agree it'll be at the 1 position. Because they should be at the 1 position, right? That the substituent should have the lower number if it's bonded to the alkene. So 1,1 dibromo ethene. All right, let's try a few more. Oh, my bad. So this one. Well, we have an alkene and an alcohol. So what did I say about alkenes and alcohol? What's the parent name? Alcohol, good. And then the alkene here, even though we have an alkene, the numbering changes. So we should number in the direction. So which groups gets the lower number? The alcohol. So 1, 2, 3, 4, 5. All right. So at the 3 position, methyl. And then where does the alkene start? 3. So could we put a 3 there? 3 pentene. All right. So So in this case, you have to use this numbering because you have two functional groups, all right? So 3-pentene dash 2 dash all, okay? So another way to write it is like this: 3-methyl pent dash 3N dash 2 all. But I'm not gonna write that, all right? I like it this way. Yes.
For the one that died at the end, so that was going to E or Z because it's symmetrical.
Yeah, and because you don't to be like cis or trans, the bromines have to be on adjacent carbon atoms, not the same. Yeah. Yeah, so there's no cis or trans isomers with this one. That's what I'm trying to get at. So you can't arrange these two where there's a cis isomer and a trans isomer. That's because you have two identical atoms on the same carbon, so you can't have any stereo relationship. All right. So let's do one more alkene example. All right. Another cyclohexene. All right, so you notice here, you might be wondering, oh, okay, is it E or Z? No, and that's because this alkene, for a cyclohexane, they're always cis alkenes, and you can see here, these two groups are locked in the ring structure. So that's a cis cycloalkene. Now, there are trans cycloalkenes, but they're very big. They have to be very large rings because you can imagine if the alkene was trans, you'll get a lot of angle strain, bond angle strain, right? So you have to be careful with that. Okay, but let's just name this as usual. So how do I number the carbons in this one? All right. So remember, in alkene, they get 1 and 2 position for the alkene carbons, but then you have to decide which one should get the 1 position. It'll be a tie, so you have to use a alphabetical rule. Ethyl substituent comes first alphabetically before methyl, so we're doing 1, 2 like that. So 1 ethyl, 2 methyl. All right, what's the parent name? You got it, cyclohexene. So when alkene has the 1 position, you don't have to specify, especially for these ones, where the alkene is. If it's cyclic, okay? Because it's assumed that it's the 1 position. All right. Okay. Well, that's nomenclature. Not too bad. So we're kind of building up our nomenclature here. From alkanes, haloalkanes, alcohols and ethers, and now alkenes, okay? All right, so let's talk a few things about the double bond, all right? So the double bond is actually electron rich, okay? But it won't do typical reactions we saw with alkanes, okay? So if you take this compound, so remember when we did free radical halogenation? Well, what if you take Br2 and then HV? Well, you will see no free radical reaction. So no radicals will form. So no free radical reaction. This will react, but it won't react in the way you expect. So very different reactivity for an alkene versus an alkane. So remember alkane here. Ethane, sorry. Remember this guy? So what happens when we shine light and Br on this molecule? What primarily happened here? So what was the major product of this? So what kind of reaction was this? Free radical. Bromination, right? So one of your products is substitution of the hydrogen atom with a bromine atom. So you get ethyl bromide, right? And a molecule of HBr. So we'll learn that alkenes don't do this similarly. They'll react with bromine, but not in this way. They won't form a single, so you won't get this, all right? So you're expecting this, right? H2CCC HBr plus HBr. This does not happen. All right, so does not form at all. So it's a different, we'll learn that they react, but not through this pathway. Okay? So we sadly can't get it through that. I wish we could, but we can't. Okay, so I just wanted to compare alkanes and alkenes. Very different reactivity, and that's because, let's think about it. What bond is easier to break in an alkene? The CH bond or the pi bond of the double bond? No, not the CH. No. So remember the CH here, remember the CH bond? We have direct orbital overlap. But what's the pi bond actually? Are they directly overlapping? No, so they have some distance between them. So the further, remember physics, the further the distance, what happens to the force? Decreases, right? Weaker force of attraction, easier to break. So the pi bond is easier to break. And we'll see in this chapter that the pi bond is what primarily reacts in alkenes. Okay? All right. Okay, so that's the kind of preview here. Alkenes, they'll feature reactivity at the pi bond, not the sigma bonds. Okay? So now let's go into some of the physical properties of alkenes. Okay? So some of these will be relevant because alkenes are also in food. So I'll mention that. All right. So compared to alkanes, similar boiling point, and that's because they're mainly just carbon and hydrogen atoms, so similar boiling point to alkanes. All right. So C1 to C4 are primarily gases. All right, so C2, C5 to C18, they're mainly liquids. So I don't know if you guys heard of paraffin oil. They're mainly alkenes. And they're used as like lubricants, fuels, for different kinds of applications. All right. And then if you have larger type alkenes, they are typically solids. So like waxes, stuff like that. All right, now we have to talk about melting point. And you should pay attention to melting point because it's important. It kind of explains why certain molecules in food are oils and why certain ones in our bodies are fats. Okay, so this is where cis and trans fats comes into play here. So the melting point is very dependent on the internal structure of your alkene. So the melting point depends on how molecules pack in the solid or crystal structure. In the crystal structure, all right, so think about a cis double bond. So let's just draw a cis double bond here. All right, so I'm just going to draw a random double bond. All right. So in reality, this double bond, what it actually looks like, once it's in this most stable conformation, it looks like this. All right, so I'm just going to draw it. All right. So what the double bond looks like is actually looks like a kink. It looks like it's bending inward. Okay. So if you did imagine here, when two of these molecules approach, the shape can't fit well in a solid state. All right. So this will disrupt the packing. So disrupts the solid packing. So disrupts solid packing. And reduces the melting point. All right, so mainly cis alkenes, they're mainly like oils. All right, so they're mainly like oils. So oils here, they don't pack well, so they don't melt. They don't form a solid. They don't form a solid there. All right, so this is what we call a kink structure. So kink structure. And if you try to fit a lot of molecules into together here, they won't fit as well. So it's like taking Legos and trying to fit pieces that obviously won't connect, right? They won't pack well, so the molecules won't spread out and just remain a liquid, okay? But in the trans case, so yeah, trans fats, though, you don't want trans fats. So trans double bonds, okay, and so a trans double bond looks something like that. Okay, so remember the hydrogen atoms are kind of coming out over here. So if I kind of do like this, oops. All right, the trans, see the hydrogens don't really collide here, and they can kind of fit better. They line up, so they're very linear, so they can line up together much easier, and they will form a solid, okay? So here we could say can pack better in the solid state, so they can pack better in this situation, okay? And you get higher melting points. So these guys are usually fats, so that's why you don't want trans fats. Okay, so it's better to kind of form cis alkenes and form oils. Those are more essential oils. Okay, and so the structure of the double bond here kind of plays an important role in the melting point. And so that's what I want to mention. So alkenes, think about melting point. Cis alkenes, they have kinks in them. They can't pack well, so they form this weird structure. Trans double bonds, they're more able to form better structures, more packing, and that's why they are typically higher melting points. All right, so let's look at polarity. All right, so you have a cis alkene. There's a dipole pointing towards the internal carbon atoms of the alkene, okay? So your net dipole is actually pointing down the center of the double bond here. So your dipole does not cancel out. So net dipole is not equal to 0, okay? So for a cis alkene, they are slightly polar. All right, what about trans alkenes? So trans alkenes, the carbon atoms are pointing in this direction. So what can we say about their dipoles? Yeah, they're in opposite directions, equal magnitude, right? So these are actually in opposite directions. So we treat this as the negative z direction, and this is the positive z direction. They're actually going in opposite directions of their axes, so now they cancel out, okay? So the trans alkenes, they're usually less soluble in water, and that's because they are not polar. So net dipole equals 0. All right, nonpolar. Maybe that's why they're kind of bad for us. They kind of metabolize through our cells, our cell wall, our cell membranes, and they get into our metabolism much quicker. All right. Okay, any questions about the properties of alkenes there? So, in general, not water soluble. They are like alkanes. There's no polar atoms. But depending on the orientation of the double bond and the substituents, they can be slightly polar. So short chain alkenes, they have some solubility in water. All right. So I want to talk about pKa because this is going to be important when we talk about alkynes. All right. So let's talk about first the order of decreasing electronegativity of carbon atoms, which might sound a little bit weird.
Professor Andrew,
Yeah, what's up?
can you explain what the -2 and the +2 is?
Oh, that's Z. This is like an axis. I was saying here, this is like an axis. So let's go back to a little math here. So say this is an axis of rotation, okay? This is the z-axis, so I was saying this is the negative z direction, and this is the positive z direction. So, since they're pointing in opposite directions, they cancel out. Yeah. All right, let's talk about hybridization. All right, so we have sp. What's the hybridization for an alkene carbon? Yep, you got it. And then how about for an alkane carbon? sp3, good. Those are the only three you need to remember in OChem, right? Simpler that way. All right, so, but what's the percent S character, do you guys remember, for sp, sp2, and sp3? So how about sp? 50. And then here, 33%, right? And then how about for sp3? Yeah, you got it. Good. So remember here, the more S character you have, that means it's more spherical. And if you occupy that orbital, electrons will be closer to the nucleus. So if you have a negative charge and it's closer to the nucleus, what can we say about that ion? Is it more stable or is it less stable? You have a negative charge closer to the nucleus, which is positively charged. So would you think that's a stabilizing force or a destabilizing force? Stabilizing, okay? That's why the acidity of these different hydrogen atoms on carbon, they are increasing if you have a higher S character, okay? So we'll just end here, okay? And next time we'll start on the stability of alkenes, like I was talking about, more substituted, all right? So order of acidity. Okay, so here we have pKa. All right, so let's take a few compounds here. Let's have a terminal alkyne, a triple bonded C bond to an H. Okay. A alkene carbon, two alkyl groups on one carbon atom, and then we have a hydrogen here and a R group. And then we have the alkane, R3C, and then we have a hydrogen atom here and two other alkyl groups, okay? So, sp3, sp2, and an alkyne, sp, okay? So, which one do you think will be the most acidic? All right, which one has more S character? The triple bond. So its conjugate base should be more stable, right? More S character means closer to the nucleus, so the negative charge is more stable. So this one actually has the lowest pKa, 25. Alkenes, it goes even higher here, 44, and then alkanes is a whopping 50. So we can say here that this group right here is the most stable conjugate base. Which one is the least stable? sp3. So here, this one, R3C, Cr2, this one. So this negative charge here, least stable. This becomes important because if you have an alkyne in there, an alkane and alkene, and you add a base, the base will automatically react with the alkyne H. And that's what gives us synthetic usefulness to this reactivity. Okay? So, just do it this way. If you have a triple bond there, the S orbital is more spherical in nature, more S character, closer to the nucleus. So here I would just put here negative charge closer to carbon's nucleus. Okay? And you have a negative charge attracted to the positive charge, more stable. Okay, so you should kind of think of it like that. All right, we'll talk about alkene stability next time, and then we'll jump into some reactions. Okay? All right, that'll be it for today.